opportunity to give a talk as well. As you can see from the title, I mean, what I'm talking about here is looking at proofs that have been generated by computers and trying to understand them, essentially. So you see a few examples during the talk. So this is, as it says here, this is joint work with Paulo Oliva, who have been working since we started working with Ursula Martin many years ago on verification of continuous systems, dynamical systems. And after that, the project of Ursula finished, we continued looking into using continuous logic to kind of develop a whole logic for dynamical systems. We thought if the system is continuous, we should probably start a kind of continuous logic as well, logic with real valued truth values. And that's how we got into this. So the questions we were asking when we started looking at continuous logics, and then because continuous logic is an extension of Łukasiewicz logic, which is a substructural logic, and we started asking questions like, is this valid in this logic? Is this provable in this logic? And A is simply a formula, and L is, imagine some logic. And the way we found to try to answer this question was to look at the algebraic semantics for that logic. So we would reduce the question to the question, is this equation true in this class of algebras? And most of these logics have a corresponding class of algebras that is axiomatized by equations. So there was this prover 9. Some of you might have heard of prover 9 and the corresponding maze 4. So this is a kind of a proof searcher and a counterexample searcher, like a model checker in some sense. And we started using these tools developed by Bill McCoon and to try to answer these questions in this class of algebras. And quite amazingly, I mean, it was really a big surprise, at least to me. These tools were incredibly successful. I mean, they would either find a counter model very quickly, models of size 5, 6, for things that we were thinking really hard, is this true or not? And when there was no counter model, so we got up to models of size, I don't know, 20, and no counter models were found, we would run prover 9, and in some cases you would find a proof in just a minute or maybe 3 minutes or sometimes 2 hours, but it was incredibly successful. So, but then the question was, you look at this kind of 500 lines of equations and you say, okay, I know it's true, I know it's provable, but can I understand this proof? In the sense that, can you look at the crucial steps in the proof? What are the crucial steps in this proof? What are the kind of the main lemmas that build up to prove the theorem? And it wasn't easy because all these 500 lines of equations that follow from each other, from prover's 9 point of view, they were completely the same. They are all just formulas. You know, they don't mean anything in some sense. But for us, in order to understand the proof, we needed to find some meaning in some of these equations. Like, what are really the important steps? What's the strategy in the proof to derive that? So that's what this talk is about. And I'm hoping that, I mean, this wasn't, we didn't set out to study this, but I thought this was something interesting to present here because I think it's very related to the topic of the seminar. So what I will present is essentially 3 case studies that we've worked throughout the years. So starting with continuous logic. So the first question we had was, okay, you have continuous logic which starts with Łukasiewicz logic, like the logic of the unit interval, and adds a halving operator. You say, well, if the formula has truth value 0.6, you also have the formula half of A, which has truth value 0.3. So the question is, the question we had was, well, is this true if you don't have classical logic? If you are in a kind of intuitionistic or minimal fragment of Caswich logic? And we were able to answer that and show that it still holds. Then we looked at, again, continue to look at these intuitionistic fragments of Vukasevich logic. And there is this really interesting theorem of intuitionistic logic that although the double negation elimination is obviously not provable in intuitionistic logic, so this is not A implies A, so this is kind of what we add to intuitionistic logic to get classical logic. But the double negation of this is provable in intuitionistic logic. And that's what kind of underpins all these double negation translations of classical logic. But this is one of these amazing theorems of intuitionistic logic that if you ask any logician to try to prove, they will really struggle. You can try for yourself. I'll show you the proof during this talk. So if you want, you can leave the room if you want to think about this before I present the proof. But it's a really interesting challenge, and the reason it's not easy is because it uses contraction. And it uses exposed quadlib, uses weakening, uses all sorts of structural rules of logic that you normally don't use. If the proof is linear, it's very easy to find proofs. But if the proof is not linear, it is not easy at all. And then once we're able to show that this also holds in a kind of an intuitionistic fragment of Vukasevich logic, then we say, well, maybe all the double negation translations also work in that kind of substructure of set, and indeed they do, so which is also quite surprising, because most of them, like the Godel-Gensen translation, the Glivencke translation, they all rely on contraction for the soundness of the translation. So the fact that they still hold in some of these substructural logic is quite surprising. But if you are not familiar with all these substructural logic, so this is kind of a brief introduction. So by affine logic, I simply mean kind of, you could think of linear logic plus weakening. So you have, you can add any kind of formulas to your context, and gamma A implies A. So that's what weakening is. You can also write it as a rule. So you can say if you prove A from gamma, then you can also prove it from an extension of that context gamma. So that's the rule of weakening. Contraction would be, contraction would be if you prove formula B from 2 copies of A, then you can also prove it from 1 copy. So it's like the number of times you use a formula in a proof doesn't matter. So that's what kind of the contraction rule say. And linear logic first gets rid of those, and then you realize that then you have 2 kinds of connectives. You have the multiplicative connectives and the additive connectives, and then you reintroduce these in a controlled way using exponentials.
What's the meaning of the tensor product? Right.
Is the multiplicative conjunction. It's the conjunction where the contexts don't contract. Hello. So, so this is essentially multiplicative disjunction, and you could say linear implication, except that because you have weakening, you could say this is affine implication. So that's what we have been calling minimal affine logic. Minimal because you don't have negation. You don't have false. And if you had false, for instance, you could define negation as simply A implies false. Because you don't have false, you don't have negation, so that's what people normally call minimal logic. But to that you can add extra things. For instance, you can add the double negation elimination and to get a kind of a classical system. Or you can add contraction, either in the form of a rule like this, or in the form of an axiom, saying that 2 copies of A is the same as A. So, and then you can add also weaker forms of those. So the X-false quadlib, saying that false implies anything, is actually a weaker form of the double negation elimination. So this EFQ follows from DNE if you have weakening. And similarly, you have a weaker form of contraction, which people normally call the divisibility axiom, saying that, so contraction would say having one copy of A is the same as having two or many copies. But the divisibility axiom simply says if you have A and you have A plus B, then you can conclude not only B, but you also get back a weakening of A, okay, so which is B plus A. So you don't really have A twice, so you can use A to get B, but you don't lose A either. So you still get back what is left in some sense. If you think of this as addition and this as subtraction, you can think of it as saying, well, if A is stronger than B, when you get B, because B is weaker, you should still have something left. And that what is left is exactly the difference between A and B. And if you have contraction, that's obvious because you can use A twice, so you use A once to get B, and you use A again to get this weaker form of A. So this is a consequence of contraction, but it's strictly weaker. So once we have all these four axioms, starting from minimal affine logic, you can build all these other logics by simply adding these things. So if you start with the minimal logics and add EFQ, you get these intuitionistic counterparts of the logic. If you add the full double negation elimination, then you get the classical systems. Now, from the classical systems, we only have here is weakening, so we have absolutely no form of contraction. But if you add the divisibility axiom, then you get Łukasiewicz logic. So Łukasiewicz logic is essentially minimal logic plus DNE and the divisibility axiom. If you add full contraction, not just the divisibility axiom, then you get classical logic. And you can do that in any order, which means you get 9 different logics. Okay. So the three on the right here are the standard like minimal logic, intuitionistic logic, and classical logic. The three on the left are really well behaved, so they are kind of simple extensions of linear logic, pure linear logic with weakening, where cut elimination still holds. You have very kind of simple kind of decision procedures and so on. Over here you have the famous kind of Łukasiewicz logic, that is the logic of the unit interval. Like, in order to check if something is provable in this logic, is enough to just read conjunction as plus, implication as negation, cut-off negation, and cut-off addition, and simply check whether the formula evaluates to 0 in the unit interval. If it does, then the formula is provable. So because you have a decision procedure for linear real analysis, the unit interval, then you get kind of I think it's NP decision procedure for Łukasiewicz logic. But these ones here, well, they haven't really been well studied, and maybe partially because there isn't a cut-free system, so these logics don't have a kind of analytic proof system. So people have tried really hard to build these kind of analytic proof systems, but all they got was proof systems for extensions of those, like for instance for Hayek's basic logic, which is just above this because it adds prelinearity, so that if either A plus B or B plus A, which is not intuitionistically valid. But once you have prelinearity, you can build hypersequence that have the subformula property and so on. But once you lose prelinearity and you are really in the realm of intuitionistic logic, then it's not easy to build these analytic proof systems. But on the other hand, these have really kind of beautiful algebraic structures as semantics. So the algebraic semantics for these logics are what people have been calling hoops, and I'll talk about this in a minute. And this is essentially what we have been looking at. So starting with minimal logics. Sorry. So the algebraic semantics for minimal affine logic is based on Pokrams, so partially ordered commutative residuated integral monoids. Okay? So you have this kind of, it's a short word, Pokrams, but it hides quite a lot of structure. So you have essentially a monoid, which is commutative because in these logics, sorry, the last kind of substructural rule that people consider is that of exchange. So if you prove C from A and B, then you also prove it from the A. So the order in which the formulas appear in the context doesn't matter, so that's the exchange rules, and these are the three kind of main substructural rules, so contraction, exchange, and weakening. And but in here we are taking exchange for granted, and we are taking weakening for granted. So that's why we have a commutative monoid. Partially ordered just means that you have a notion of strength, which is for us is logical implication. So this is actually definable from the arrows. So x bigger than y just means x implies y is 0. So x implies y is true. And say that this is partially ordered, it means that this respects this. So if x is bigger than y, then x plus y is bigger than x plus z is bigger than y plus z, and so on. And integral just means that 0 is the least element. So anything implies true. So 0 is true here. But you see that we don't have false. So this is minimum affine logic. If we add false, we add a 1, like a top element to that order, and you get bounded Pokrams, which are the algebra for intuitionistic Ukazovich logic. So intuitionistic affine logic. But then you're moving from the left to the right, adding the divisibility axiom to the algebra corresponds to adding divisibility in to the algebra as well. So if you start with the Pokrams and you add this axiom that says, well, if A is bigger than B, then you can write A as B plus B arrow A. Again, having it as intuition, if you think of this as addition and this as subtraction, it's saying if A is bigger than B, then you should be able to write A as B plus something, and that something is exactly A plus B.
So, do people in this area really write arrow? I sort of would be expecting them to write truncated subtraction and call it modus, but is that?
No, they do actually write the arrow. Yeah.
But it is a kind of subtraction. Right?
Yeah, it is, but you can also, because you see, I've written this as multiplication, because if you write this as multiplication, then this is actually division.
Yeah.
So if I had written a plus here, that would be really subtraction, but you also have the other hoops where you interpret the tensor as multiplication and the arrow as division. And that's why they call this the divisibility axiom, actually, because this was actually the original motivation.
And the word, you're going to explain where the word hoop comes from?
I looked at the Buch and Owen's manuscript. This was never published. And they don't give a very good justification. They just say, well, let's call these hoops. So yeah, I'm afraid I don't know what was in their minds when they came up.
So I was expecting some kind of circular thing.
Yeah. I don't know.
Reference to loops?
Sorry?
It's a reference to loops?
Well, I have a copy of the manuscript. I can show you the passage where they suggest the name, but it doesn't really say anything.
I mean, a hoop should be a higher order.
No. It's just because it rhymes with something else, and it's like completely arbitrary. But this you can define this as an equation as well, and which means that you have a purely equational semantization of this class of algebras.
And it is, sorry to keep on asking, is there a connection with MB algebras?
Yeah. So it's here. So the hoops are the algebra for what we have been calling minimal Ukazovich logic. If you add a top, and you get bounded hoops. That is what we've been calling intuitionistic Vukasovich logic. And if you add that every element, so if you add that x equals the double negation of x, these are evolutive hoops. These are essentially MV algebras.
Yeah.
So it's not the same because they are over a different signature. MV algebras is normally defined using arrow and
But they're
just arrow
equivalent
indication.
categories, I suppose.
Yeah, but they are exactly the same kind of structure. So evolutive groups would be MV algebra. And yeah, and then here, I mean, I don't know, just you have the Boolean algebras, the Haitian algebras. These are kind of the algebras for minimal logic. I'm not sure what people call them. I just call them Brouwer algebras, but I don't know, maybe there's a better name. Someone might know. Try to find it. But these are essentially, Pockrims where you add that x equals x plus x. You add that equation, you get this. If you add that false implies everything, you get the Haitian algebras, and if you add that x equals double negation of x, if you add the involution, then you get Boolean algebras. So that's what we can do. We can say, well, if checking whether something is valid in a logic is the same as checking whether some equation holds in one of these algebras. So as I promised, I have 3 kind of case studies. So the first one was on continuous logic. So if you look back at that kind of 2-dimensional picture I showed you, the 2 axes are contraction and classical logic. So you can either add contraction, you can add classical logic, like the double negation elimination. But there's also a 3rd dimension, which is adding a halving operator. You add a kind of, for each formula A, you add a modality half of A. And the interpretation in the unit interval is simple, but then when you go to kind of fragments, like in minimal logic or in intuitionistic logic, then this is just something that you axiomatize as this. So that's the axiom. Half of A is the same as half of A plus A. And again, here, if you think of implication as subtraction, that is just saying half of A is A minus half of A. So that should axiomatize half of A. And in classical logic, so if you take Vukasovich logic and add this, it's easy to show that this uniquely determines the modality, meaning if you add another halving operator with the same axiom, you can prove that you were the same. And that's what people have called continuous logic, essentially. But how about if we add these to the weaker logics, like minimal Vukasovich logic or intuitionistic Vukasovich logic? That's what we ask. And we thought about it for a few weeks, looking at this and trying to think about counter models and so on, until Rob Arton said, why don't we try this on a theorem prover? And he was familiar with prover 9, and he said, let's try that. And prover 9, it works really well for equational logic, so it has a very clever kind of tactics. It was developed by Bill McCoon, and it uses resolution paramodulation. Not probably you are all experts on this, but essentially it tries to derive. It starts from the axioms and then the negation of the goal, and it simply tries to derive new equations using the old ones by trying to match the left side of one equation with a sub kind of formula of the other equation, and if it finds a match by kind of unification resolution, then it just replaces that sub formula by the right hand side, and it adds that as a new equation and keeps going until it finds a counterexample, until it finds a contradiction. You get 0 is different from 0, you stop and say found the proof. So that's what we did. We say let's try this with prover 9. So we say let's add these implications. So they're saying x is equivalent to x implies a, but y is also equivalent to y implies a, and we wanted to, from these 2 assumptions, show that x equals y. Not in classical Vukasovich logic, but in minimal Vukasovich logic. And after about 3 minutes, while we're having a coffee, the thing beeps and says, proof found. It's like, how is that possible? We spent 3 weeks and got nowhere. So our job then was to try to understand this proof. Like, what does this mean? And you look at these kind of 200 lines of equations, and you try to understand. So what we managed to get was, this was kind of our first attempt, was to say, well, let's look at all these equations and see the ones that we think are like natural kind of looking equations that mean something to us. And let's take those as kind of lemmas. And it was quite kind of arbitrary. You just look at them and say, oh, this looks interesting. This looks like there is some symmetry here, so maybe that's an interesting equation.
It's not arbitrary, Paulo, it's deep learning.
Yeah, deep
Remember,
learning.
it's deep learning.
Deep learning, yeah. So that's what we were doing. So, but essentially, you break these into like 200 lines into like 9 sub-lemmas that you think these are like the crucial steps, and then you prove those. And each of those has like just 2-3 lines of proof, so each of them is quite simple. And using those, you can then simply prove your theorem with a one-line proof.
So you need 1 to 8 to get 9, do you?
Sorry?
Do you need 1 to 8? To
Exactly. So this is essentially kind of taking the proof or 9 proof and trying to find kind of the checkpoints that we thought were interesting. And indeed, 1 implies 2, and 2 implies 3, and so on. So this is kind of still kind of not very interesting from our point of view, because it's essentially doing a little bit of abstraction from the proof that we got from proof or 9. These lemmas are still not very intuitive. I mean, 4, for instance, seems quite arbitrary, and but we thought this was kind of what, yeah.
So you mean that the structure is linear? There is no thing that are dependent?
Well, you could write it as a proof tree, but proof of 9 gives you a sequence of equations, and each equation follows from some of the equations below. You can kind of unwind it into a proof tree, but yeah.
Is it a tree or a graph? I mean, there are some things you...
Yeah, some things you use twice,
If
or
you-
many times.
Yeah,
Yeah, so it's more like a tag. Yeah.
Did you draw the graph?
No, we didn't. We just found some things that we were interested in. We proved them on their own, found the proof. I tried to understand this proof because these were normally very simple and short proofs. And then we added those as axioms, extended the theory, and then tried to prove again, and so on. So it was an iterative process to try to then finally get a one-line proof of the result. So this was, as I said, our first attempt. But then once we succeeded, we said, wow, that looks quite interesting. So we said, how about let's forget continuous logic and look at these intuitionistic fragments, these logics that people haven't really studied well, and see what happens there. So our first question was, well, in intuitionistic logic, this holds. So as I was explaining in the beginning of the talk, does this hold if you don't have contractions? So here is the, I'm going to leave the room now. Here's the proof of this, the negation, the double negation of the double negation elimination in intuitionistic logic. Right? So the reason is, as I was saying, this is tricky, is because you think, well, to prove this, you assume the negation of not A plus A, and you have to derive false, right? So that's what you have to do. There is no other way. So you say, assume this and try to derive false, but the crucial thing is that you really have to assume it twice. Because if you don't, if you only have it once, then to get false, you really need to prove this, but you don't have a proof of not A plus A in intuitionistic logic. So there is no way to carry out this proof using this assumption only once. In fact, this fails in affine logic. But if you can use the assumption twice, it's possible, because what you do is you first use that assumption to derive not A. So this is stronger than not A. But once you have not A, you can derive not A plus A. So you can't prove not A plus A outright, but you can prove it from the assumption not A. And the assumption not A does fall from not A plus A, because this is simply a weakening of this. And then once you have this, you will use that assumption again to derive false. So it's quite intricate because then once you discharge those assumptions, that's where your contraction happens. So you've used this assumption twice, you used the exposed quadlib, and you've used weakening. Okay, so things that if you're doing a proof search, you hope that you will only need introduction and elimination rules, and things are kind of straightforward because you know that there's only one rule to apply. But if you have to use...
So if I ask a functional programmer to write down a CPS, thing, that's a good exercise.
That would be a really big challenge. So that's something for a functional programming exam, yeah, like to test the HTTPs. So, but then you ask, well, we know that contraction implies the divisibility axiom. Will the proof still go through if I only have the divisibility axiom, not full contraction? And in fact, it does. So I just want to show you the process of doing this. So here is the axiomatization of bounded hoops in Prover 9. And this is kind of the goal. So you say you define a macro for negation and the macro for double negation. And then you add your goal saying that the double negation of double negation implies x is 0, so it's true. And you run this to Prover 9, and it just keeps generating equations from all ones. So using this resolution, paramodulation. And this one actually finds a proof in 55 seconds. That's why I'm showing you this.
Is this vanilla Prover 9, or you need to twiddle with the options to...
No, it's just, I'll
Without
talk
it?
about this, in a few minutes. But this was just, we're not experts on Prover 9. So we
Just
simply,
Prover 9 without any...
we axiomatize and then we just run the tool without any tactics or anything. And it's just like, you can see here that we are already in like 1,500 formulas generated. And I think at about,
Is the printing the bottleneck here?
it could be. No, it takes 50 seconds even with the printing.
It runs deterministically, the default settings.
Yeah, it's deterministic. So yeah, that's it. Exiting with one proof.
61 seconds.
61 seconds, yeah.
Yeah, the video is slower.
The video could be. But this is the proof. So it generated 38,000 equations until it found a derivation of false.
Also can you show the length of the proof?
The length of the proof, yeah, I have a cleaned up proof
49.
for you to see. So result. So you have another tool that cleans up the proof. So it's actually 109 steps. 109 steps, and you get the proof. And you think, well, what does this proof mean, right? So you have 109 equations that each follow from each other, from the previous ones, and you say, can I understand what this proof is doing? And that's what we try to do. So as I said, we were able to find this proof, but initially it was like, okay, we found a proof. So all we know is really that it's true. It doesn't really tell us anything deep about why it's true. So that's kind of what we saw. But then, as we did with the kind of case study in continuous logic, we try to find kind of patterns. We try to find things that look interesting, looking for commutativity, distributivity laws, and so on. And then we noticed that if we extended our language, if we extended the signature with what we have been calling like these defined connectives, then some of the equations actually made a lot of sense. Okay, so you have so formulas like A tensor A implies B. Okay? So this formula kept appearing throughout the proof. Also, B implies A implies A. Right? It's kind of the continuation monad. Kept appearing again and again. And we say, well, then we notice that the divisibility axiom is essentially saying that this is commutative. So if you define this as kind of a weak form of conjunction, and we call it weak conjunction because this follows from A tensor B. So the normal conjunction is A tensor B, and this is weaker because it follows from A tensor B, but it's a kind of a conjunction because it implies A and implies B. You can get A by simply forgetting this, and you can get B by modus ponens. So this implies A, implies B, but it's weaker than A tensor B, so we call it a weak conjunction. This, on the other hand, is kind of a dual of this, is a strong disjunction. Then also this thing kept appearing, like an implication where you don't forget the assumption. So you have A plus B as your kind of normal implication. But then we saw it all the time, this A implies A times B, which is a kind of a strong implication. It's saying it's an implication where you not only can go from A to B, but you can keep the A. Okay? And this is kind of the magic of the proof, that you are able to prove things without losing the assumption. Okay? So if you only have A plus B, you apply modus ponens, you essentially lose the A. You get the B, but then you lost the A. But if you have a strong implication, A implies A and B, then once you prove A, you can do modus ponens and get the B, but still have the A. And that's how the proof essentially was able to prove things like this without using contraction, without using full contraction, but only the divisibility answer. And also things like this, that initially we thought was kind of strange, but then we realized that it's a kind of a norm. It's like, normally you would say not A and not B, but this is a kind of a different way of saying it, saying not A and B implies A. Okay? So by modus ponens or by composition, again, you get not A and not B, but only if you have contraction. If you don't have contraction, that's all you can say.
Are all these things commutative?
So this is commutative in minimal intuitionistic, minimal Vukasovich logic, because that is essentially commutativity of this is the divisibility axiom. Commutativity of this is what axiomatizes classical Vukasovich logic. So in minimal and in intuitionistic Vukasovich logic, this is not commutative. This is, although yeah, this is a bit misleading to write it as an or, because in minimal logic and in intuitionistic logic, this is not commutative.
Would you like to pronounce the last word on your slide?
I think it's unfec. But
So is it amfec or is it ampec?
anybody knows?
And what's its etymology?
I think it's.
Is it like ampersand? No.
No, I think it's studied this nor as it showed that this is a connective that defines all the other ones.
Yeah.
So it showed that the nor is really special because once you have the nor, you can define any other connective, and that's why people call this nor the Persis anfac, because he called it anfac. I think it means cuts both ways.
It's from a Greek word.
Greek word, yeah.
Charles Sanders Peirce.
It means cuts both ways, right? Oh, so,
Oh,
Yeah.
thank you very much.
Double edged.
Very, very educational.
double wedged, yeah.
So is this MFA commutative?
So this is commutative, yeah. This is one of the things we're able to prove, and it's not trivial. So this is kind of the process we follow. So we start with kind of the initial proof that prover 9 gave us, and try to spot these kind of patterns, these connectives. And then once we kind of identify this connective, we say, well, let's look at now properties of those connectors, like commutativity, distributivity, and so on. And then get prover 9 to prove those kind of those properties on their own, try to understand those proofs, and then expand the theory, add those kind of as lemmas, and then try to prove again. So until we got shorter and shorter proofs that we say, well, actually now we can understand the proof. This is just a consequence of those.
So what's the prospect for cutting the humans out of this loop? In other words,
That's
getting a machine to try and do what
yeah,
you just
exactly.
did,
That's part of my concluding slide.
Oh,
It's
right,
like
okay.
like saying, well, how much of that can actually be done automatically with a bit of machine learning and deep learning? So,
So but this means that you think that prover 9 will find a shorter proof if you add lemma.
well, it might not find a shorter proof. It actually might be a longer proof, in the sense that you have more steps. But is a proof that humans can understand because it's broken.
Yeah, but if you had lemmas, you could find the previous proof, and you have.
It could find the previous proof, but because the prover 9 search is kind of trying to be clever, it could go in a different direction and find a different proof. So it doesn't mean that we'll get exactly the same proof as we started with.
You might be able to drop the definition from that dilemma.
And in fact, even if you change the order in which you list the axioms, you get different proofs.
Oh shit.
Because the search is like it uses kind of the axioms in the order you're given. I'm not an expert. Maybe you know more about how this.
But did you use this trick to put your new lemma first or last?
We tried a few things, but once we had a proof we understood, then we were happy with it. It wasn't really our goal to get the shortest proof, but rather try to understand the proof. But this is, for instance, the proof that the double negation of the double negation elimination holds, and it simply uses the commutativity of the unfact. Okay? So this is one of the lemmas we're able to prove, and this is there it is. Right? So the theorem 4.7. So the proof of this actually goes through to this, plus some other lemmas.
But that does deeply remind me of, if you look in the MV algebra literature, they by hand do quite a lot of clever algebra, and it actually does hinge very often on something that doesn't look commutative. One of the axioms says something is commutative that wouldn't normally be, and then that enables you to prove things that you wouldn't. So it actually rings lots of bells.
Yeah.
Yeah.
Finally, the last one was that once we knew these holds in intuitionistic Łukasiewicz logic, they said, oh, actually, then it means that we probably can do all these double negation translations in the substructural setting. So double negation translations allow you to go from classical logic back to intuitionistic logic and even sometimes to minimal logic. And the question we had was, how much of those actually hold if you don't have contraction? Because some of those, as I said in the beginning, rely on the contraction axiom. So here are some of some examples. So for instance, if you start with a formula like this, the Kolmogorov double negation translation simply places a double negation in front of every subformula. Okay, so this formula would be translated as something like this. And in fact, although this is kind of really an overkill, the advantage is that then it doesn't rely on contraction. The Kolmogorov translation goes through even in affine logic. So that's kind of the advantage of adding all these negations, because then essentially you don't need to think. The proofs go through quite easily. But then you have other kind of more economic double negation translations, like the Gensen translation, that simply negates atoms. And you have the Glivenko translation that simply negates the whole formula. And what Gilda Ferreira and I did recently was to try to understand the relation between these double negation translations. And what we realized is that these kind of translations are simplifications of the Kolmogorov using these properties. Right? So if you can shift double negations outside or inside over conjunction and implication, then starting from the Kolmogorov translation, you can either shift all of them out and get the Glivenko translation, or shift all of them in and get the Gensen translation. Okay? So this ability to shift double negations in and out of these connectives is what allows you to get these different translations from the Kolmogorov translation. Now the question is, can this be done with the divisibility axiom? We know this holds in, you can do this in intuitionistic logic. By intuitionistic logic, you have contraction. Okay? So in particular, for instance, going from the right to the left here looks really tricky, because in linear logic in general, it's not possible to get a tensor out of a formula that's not a tensor. If you have A plus B, and you want to write it as, I don't know, A prime tensor B prime, it's not possible, because how do you get a tensor of something from something which is not a tensor? Linear logic is not possible. In intuitionistic logic, it is because you have contractions. So you can say, well, with this I can get the A by some proof, and I can also get the B by some other proof, and you get A and you get B, but then you have used the assumption twice. So in order to get there, so again, we proof of nine found a proof of these kind of properties, but now it took, I think in one of the proofs it took about 2 hours. It's 2 hours of kind of equation generation, and then we had 400 lines of equations to analyze. And what we soon realized is that there was a lot of kind of De Morgan properties built into these proofs, and these were kind of towards the bottom of the proof. It was like, it was building up to these De Morgan properties and then using those to derive these kind of homomorphism properties that you can shift double negations in and out. So we said, well, let's focus on these properties. So proving that the negation of a conjunction is the implication with a negation, and then the negation of an implication is the tensor like this. And this is really the hard result here, especially the left to right implication, as I said. It's really difficult to see how to get a tensor out of something which is not a tensor without using contraction. But once we had those, we realized that actually you could get more, because you could also get De Morgan properties for the derived connectives. So we had the weak conjunction, the strong implication, and they also are kind of dual to each other. So the negation of the weak conjunction is the implication, is the strong implication of A with not B. Exactly the same, but now the defined conjunction with the defined implication. And moreover, we are able to show that actually, although you don't have the commutativity of this, once you have the negation, you do. Okay? So although you don't have the commutativity of A or B, because they are De Morgan dual, the weak conjunction and the strong implication, and the weak conjunction is commutative, you get that the strong disjunction is commutative under a negation. This follows from these lemmas. And we also derived that the unfact is actually definable from the weak conjunction. So then we were able to prove this and show that all these double negations hold. Then once we were done with this, we started thinking, well, we have all these derived connectives, we have an implication, we have a conjunction. Are these kind of residual to each other? So does this weak conjunction residuate the strong implication? So is it true that this holds? So again, we fed this into Mace, and Mace wasn't able to find a counterexample. Looked for models of size 25, 30, and nothing. We say, well, let's try prover 9, and then we spent hours and hours running this, adding different lemmas that we thought might help, and nothing. I think I even left this running for a week. My laptop was kind of almost going set on fire, but nothing. So we say, well, throw the towel and contact Bob Veroff, which is an expert in prover 9. After 2 days, he comes back to us with the proof. Here's the proof. And we thought, how did you do it? He said, well, there are these kind of clever ways of tweaking prover 9. And he developed a whole theory of proof sketches that you get old proofs and try to kind of automatically spot kind of crucial steps in the proof, and then you add those and kind of interactively, I don't know. I'm not an expert on this, but there are these ways to actually maximize the power of these tools. And now we know this is true, but we still haven't found time to actually get a human read book proof of this. But this is really interesting, because then this also means that, not only you have a hoop, but once you look at the derived connectives, you have the residuation as well, which means you have kind of this residuated monoid as well, definable residuated monoid inside, which might have other properties. That you might say, well, you have a hoop, that inside you have another hoop that has extra properties that you might use. So I think that's really interesting, but we haven't really followed this.
So how many steps is this proof?
This one is, I can check, but I can't remember the top of my head.
It's actually a hoop. Do you have the visibility for the derived connected?
We haven't really looked at all the properties of these derived connected. Let's say we could ask, is this also a hoop, like and so on. My guess is that it might even be a hiding algebra, because you might have contraction, but we haven't had the time yet to actually investigate these derived connected. I think it will be a really interesting project. That's it. So as a conclusion, the key things we did was actually trying to find the abstractions. You look at these proofs, all these, from a proof or 9 point of view, all these equations, as I say, are exactly the same. But from a human, you can try to recover, to see what are the kind of the crucial steps, try to recover the intuitive kind of proof plan. And then here comes to your question, like how much of this can actually be automated? Could we have another tool that does what we did automatically? Trying to looking for symmetry, distributivity, recurring patterns. I mean, there are kind of deep learning tools that should be able to do that quite easily. So that's another project that one could follow. But really, I mean, a big thank to the late Bill McCune for these amazing tools that allowed us to do all this. Any other questions?
Thank you.
Yeah, so this it's a very nice piece of work. This kind of reminds me of experiences that I had when I used to do group theory. This thing of using a computational tool to give you a helping hand, but then it was possible to write the paper without without the computational tool being visible. And there are two particular examples that occurs to me. One is in group theory, you're often trying to prove results for all primes or all sufficiently large primes. Well, the computational group theory software at the time still couldn't really cope with arbitrary primes, but you'd run the computation for a big enough prime, 5 or 7 or something, to look generic, and that would help you to figure out what the heck was going on, and then would inform your writing of the paper. But the other thing is, I remember looking at some of this equational stuff from people who are working in varieties of groups or funny axiomatizations or things like that. And I think that was some of the early McCune stuff. And what that did was prove these results by wonderfully complicated equational reasoning of the kind you could hope to do unaided. But then you look back at the papers of the 30s by Tarski and Bernard Neumann and so on, and they didn't do it that way at all. What they did was identify some utterly evil formula and say, yes, but applying this formula is surjective or bijective or something, and therefore follow the properties that you want because you've identified this monster. But then you're coming up with a sort of higher order proof, which is never find by these tools. Although again, those tools might help you identify the hideous thing that was going to do the business for you.
Yeah, it's really, I mean, going back to your point about the primes, I mean, whenever there was a counterexample to anything we kind of conjecture, it was size 5 or 6.
Yeah.
If there was no counterexample after models of size 6, it was provable. So that's kind of an interesting, maybe we didn't come up with deep enough conjectures to find kind of tricky models, but yeah, it's...
So, but are you suggesting that computer proofs are actually more intuitive than human ones?
Well, no, I wasn't making that point really. I was just saying that there are many ways of using a prover or other software when doing mathematics. And I once looked at it was the Journal of Symbolic Computation. Just for fun, I looked at papers that use GAP, which is the main computer algebra, computer group theory kind of software. And I looked at the sort of stylistic conventions around using GAP in a paper. And you never got a paper that said, I did this big computation in GAP, here it is, the end. You always had to wrap it up in something to, you know, present it as some piece of human endeavour. I've forgotten the details now, but there seem to be, you know, 4 or 5 ways of wrapping it up so that you referred to GAP, but you've made it clear that the human had done something of intellectual merit, which you sort of had to do to get the paper published in the journal, I guess. My computer did this interesting thing, cool look, didn't quite do it.
Do you have a question?
Yes, there's a theorem that every classically false formula is provable intuitionistically. Do you think something similar holds for the other 2 columns?
Every classically false formula
Yes.
holds intuitionism.
Yes.
No, that's, I think he's saying that if you can prove not A classically, you can prove not A intuitionistically.
Yes.
Oh, I see. So every negated formula.
Yes.
Yes, I mean, false would be a good example.
Yeah, I think this follows from the Glivenko translation, right? So if you can prove, so the Glivenko translation, if you can prove A classically, you can prove not A intuitionistically. But if you start with not A, the translation is not A, which is 3 A's, which is the same as 1 A.
So as long as you can get the formula to the left-hand side of the sequence, you're happy.
As long as the Glivenko translation works, it's fine.
Yes. So
If it works in affine logic, I think the Glivenko translation fails in affine logic. So I don't know. Maybe not. I don't think so. I can come up with a counterexample. I don't think so, because the Glivenko translation actually fails for affine logic. Only holds for Lukasovic logic.
A question. So you talk about finding the right abstractions. How do we know which ones are the right abstractions?
Yeah,
and
so
whether things are the same
that's kind of what part of us being intelligent and try to find what looks like. But I mean, for us, it has been really like the recurring patterns. And if you find things that appear often, you think, well, let's look at these and add these and kind of think of them as derived connectives. And if you have properties in the proof that look like interesting properties, like commutativity, then you know you found the right notion. So if you find something and then there are no lemmas about this thing that you found, then it's probably not interesting.
Yeah.
So,
Just 1 second.
Yeah, well,
just 1 second. Andy, did you have something to add to that?
Well, I was just going to say the truism that, of course, the right abstraction for you might not be the right
Yeah,
one for me, because it reflects your background. If you have say a background like Ursula in group theory, as it were, you would recognise certain things by analogy, as it were.
For us, we were mainly guided by like symmetry, distributivity, and
Yeah, I mean, my point was that some of those derived operators were quite difficult to understand on their own. So of course you can find ever increasing
exactly.
derived operators which might have
You're
certain
right,
properties,
yeah.
but it doesn't mean that they're easy to understand.
Cameron, then you.
Yeah, one thing along those lines that I've heard Michael Kenyon and Bob Biroff talk about, it also in the context of sort of factoring out human readable proofs, is that with Pruger 9 especially, maybe because of this sort of sensitivity to the order in which things are done and just things like that, you often need to balance like interestingness with also the rate of combinatorial explosion. So like in your case, the commutativity seemed to be very helpful, but it seems that often like commutativity of more basic operators are such that they're not so interesting, but would really cause a huge explosion of things that lead Pruger 9 down that path. And so sometimes removing things that are just likely to lead it down dead ends could be as important as identifying
that's a good point.
Yes, sir.
Yeah, so I have a couple of commands. So one about this, sort of how do you generate the interesting stuff? So we did like 8 years ago when David Stanovsky found some new open conjectures by Krug 9 and Waldmeister, and he got this huge printouts, which are 20,000 steps actually was the proof. So we really try to do it statistically by defining, by using things like substitution trees and looking at frequency counts, modular generalization of the concepts appearing there, and then trying to basically define those concepts which would under some metric shorten the
Yeah, I mean, you're absolutely right. Here we had 200 lines, so you can do it by hand, but if you have 20,000 lines, then
so we have a paper in Alpine like 7 years ago about that, and it sort of works, but it doesn't do much. The other thing that that might be relevant for this is really statistical conjecturing, which we are recently doing. And that's the sort of thing when you are taking a pitch corpus and exactly you are trying to look at things like commutativity. That's some sort of abstract property which appears very often in the proofs and seems to be very useful. So you take a huge corpus of proofs and basically try to extract such properties automatically and then instantiate them for your particular symbols based on some sort of similarity. And that might sort of very clear, I mean, it could give you something more than just commutativity and distributivity or whatever else you have there. But I agree, like finding.
Yeah, I mean,
finding
all
these
the
things,
goals that we were kind of, all the conjectures were kind of, we came up with those and tried to, but I think what you're saying is that also even the conjectures could be automatically.
Yeah. Also, not just the conjecture. The first thing I was talking about is really finding new concepts by basically looking at the things that you are doing in the proofs and coming up statistically with definitions which make them short. And if I'm not totally mistaken, this is how the Robbins conjecture proof was sort of tweaked into something readable by Godin long time ago, 20 years ago.
I have a question related to that. So here you're using Mace and Proven 9 independently. Is there any advantage to really having them in some kind of tight loop? For example, if you have a conjecture, you could quickly test
for a long time, this was the decision procedure for this kind of logics, was to run those things in parallel, and one of them will stop essentially.
No, but you could, for example, I mean, there's work done actually by a fellow graduate student of mine.
For different lemmas.
Boyomore does generalization. You look for a counterexample before you to filter out the bad generalization.
That's a good question. Yeah, I think I see what you mean now. So while you're doing the proof search, you use Mace 4 to kind of maybe cut off some branches, right? This kind of.
Or just come up with just spew out some conjectures and say which of these have counterexamples.
Actually, that's a good.
Yeah. There's an option in Pure 9.
Is there an option to?
Bill McHugh, like did it in 2005-06 when you have a bunch of counterexamples from like Mace. You can steer the proof search in Pure 9 by semantic evaluation.
Using Mace 4.
Yeah.
All right, so there is a way.
So when simplifying these proof traces, because you said, okay, this is in fact some simpler connective. Did you do it by hand, or did you have some computer support for this?
For doing
what? So you have these 100 steps, and then you say that this is actually just a weak or a strong version of the other connective. Yeah. So I would try to rewrite it to simplify what I was looking at.
No, so once we say, well, this looks like a property of the strong disjunction, right? And then we would take this and then just run through Proven 9 again and find the sub-proof. You could look through this proof as well, but we thought, well, let's just find the proof for this and then try to understand that proof and then add that as a lemma and then run again. So we did that by hand.
Last question.
So is there any special thing about Proven 9 compared to any other?
It was the one we used. Yeah, I mean, we, as I said, we didn't start out with the aim of using these tools and doing a study of these tools. It was really trying to understand these algorithms. And then it just turned out that Rob Arton knew about Prover 9, and he knew he was very successful with equational theories, and we said, let's just try it. It wasn't, it was, I'm sure there might be other tools that could do even a better job. Yeah. We haven't tried actually any other tool. We were so impressed by Prover 9's performance that we just carried it on.
Okay, so thanks a lot. I should remind all the speakers who have spoken at any point on this thing to upload their slides, and speakers who are going to speak in the future to make sure they have abstracts, because the people choose to attend or not the talks based on the abstracts, so it's important.
That's why people don't give abstracts.
So 1:30 years of full talk on machine learning.